Swayam Prabha. Digital India. Educated India.
Hello everyone. So, in last module we have discussed the test protocol for TDM testing, dynamometer for cut protective fabric testing. So, this we have already discussed. We have mandrel, then fabric is placed and cut through distance is measured. Okay. And here at for a given load n, we measure the cut through distance in millimeter. Now, let us try to see the interpretation. So, the data interpretation are done of two types based on the method, either ASTM or ISO method. ASTM method we follow that logarithmic value of this cut through distance. So, calibration D0 we have discussed. Here we first calculate the sharpness index, and from the sharpness index, if we multiply the sharpness index with the calculated cut through distance, we will get the normalized cut through distance that we have discussed here. And then we have discussed there will be one straight line relationship with logarithmic transformation of the normalized cut through distance, which is y bar. So, which is a log of normalized cut through distance, and B 0 is the intercept of the straight line, and B 1 is the slope of the regression line, and where x is the applied load. So, from that we can calculate the load required for a certain distance. So, cutting load we can calculate using this, just rearranging this equation, we will get this cutting load. So, calculated cutting load is measured here in gram force, and y r here is the reference length. So, reference length is there. So, is the, and from there we will get it is basically it is if you assume it is a 20 millimeter, then we will calculate the cutting load. So, this is the data as we have already shown the data, and column B is showing that it is a weight and measured cut through distance is C, and when we multiply by the sharpness index, we get the normalized cut through distance, and the log transformation is given in the column E. Now, from here, as we know the relationship, we will go back to the earlier. This is the relationship. Here we can calculate the slope between the weight and the E log of the normalized value. That slope of that curve is calculated here, and then intercept between the weight and the log value, log of normalized, this is actually here it is a B 1 and intercept is B0, that we are calculating. So, here you can see in this equation, this is B1 slope and B0 is the intercept. That we have calculated, and then cut through distance we can calculate using this relationship. Now, let us try to see how the data is analyzed. So, by analyzing this data, we can calculate the cut through distance using this relationship. Now, graphically let us try to understand the interpretation. So, this is the actual value of normalized distance, normalized cut through distance, the individual values. So, if we see the plot here, so at 400 load we have the normalized value 44.3, 42.47 and 48.82. So, 48.82, 42.47 and this one is 44.3. Similarly, for 60 load 60 we get these three values. For 600 load, we have these three values like 23.23, 26.45 and 24.19. Similarly, for 800 load, the weight 800 for 800 gram force, this is the three loads we are getting 12.80, 9.03 and 11.72 here, and for say 1000 we are getting, this is a 1000, we are getting 2.04 and 2.69. So, using all this data, if we plot one regression line, so this is the line we have plotted. Now, in x axis it is a log of load. So, it is a normal load, this is the load in gram force, that is a B, and in y axis it is a normalized cut through distance, it is a, there is a column B, this is column D. So, here as per the definition of this cutting load is that the normalized cut through distance should be 20 millimeter. So, let us see for 20 millimeter, for 20 millimeter we are getting this, if we draw one horizontal line parallel to x axis, it will intersect the curve at point, this point say x, and if we draw a vertical line, this is intersecting at 615 gram force value. So, this gram force 615 is the, this is the cutting resistance, that is the this is cut through distance, this is the cut through distance. Sorry. So, at here, so this 615, this is the, this load is that is the value. So, 270 200 is the 20 is the cut through distance, and here this is actually not the cut through distance, this is the, this value is the load, sorry, cutting load, cutting load in gram force. Okay. This is a cutting load. So, typically it is around 615 So, the same data we are getting here. So, 615 okay, the cutting load. So, at that load we get the normalized cut through distance of 20 millimeter. This is as per the standard. So, this is the cut resistant value. Similarly, this is used for ISO system, and in case of ASTM we use the logarithmic value of normalized cut through distance. Now, you can see this is the normalized cut through distance here, this is the calculated cut through distance multiplied by sharpness index. So, this table is calculated here. Now, if we convert it to logarithmic value, the normalized cut through distance, this is E and here it is a B. So, if we see here, it is a x axis is the gram force and y axis is the normalized log value of normalized cut through distance. Now, here if we get for 400, if we take the log 1.65, 1.63 and 1.69, this is the value. For 600 load 1.37, 1.42, 1.38, these are the load, and for 800 it is 1.11, 0.96 and 1.07, this is the load, and for 1000 we are getting 0.31, 0.43, this is the value. So, from here if we see, if we plot the straight line, so this data are basically here we can plot a straight line equation, and this equation as we have already discussed earlier, this is the equation where the normalized values are used. So, that is y dash, okay. You can see that is the relationship here. I will get this is the relationship, okay. So, y dash b 0, okay, plus x b 1. So, that is the equation here. This the slope here it is a b 1 and b 0 will be the intercept at y axis and y dash, okay. Y dash is the x axis, y axis here, which is log of normalized cut through distance. From here we can calculate x value for a particular normalized cut through distance, and if you see here this is the point, it is typically 1.31, which is nothing but log of 20 millimeter, okay. So, there is a log value of normalized, it is 1.3, and from that point if we draw the horizontal line, then it is a, but at the point here it is at 615, it is intersecting with the x axis. That means, for both the cases we are getting, even if we are using normalized cut through distance or we are using the logarithmic value, effectively we are getting the same load, cutting load. So, when we are using TDM, we can test, we can interpret in different ways, but ultimately we will be getting the same data. So, this is used for ASTM. Now, if you see, this is the normalized cut through distance log, using log, and here it is a the data we are using here, and you can see for both the things, here it is a 20 millimeter, here log of 20 millimeter, which is typically around 1.3, and they are intersecting at this point. Okay. This is the intersecting point, and when we draw the vertical line which on the x axis, they are intersecting at the point 615 exactly. So, this we have already discussed. So, both cases have cut performance is 615 gram force. Now, the next technique is that next process is the EN 388 2016 Coupe method. This method is entirely different from this TDM method. This Coupe method here, it is a traditional European standard here. Here normal load is applied, okay. Certain standard load is applied here, and this blade is not flat, it is a circular blade which rotates, okay. And at the same time they make traverse. Now, this is a traditional European test using rotating circular blade that oscillates back and forth. So, this moves like this, back and forth across the specimen under standard load, typically 5 Newton load is applied. So, adopted in EN 388 1994 and 2003 as a preliminary cut test worldwide, and then afterward it is actually a Coupe test method adopted in 2016. The EN 388 Coupe test is a method for measuring the cut resistance of particularly for protective gloves, because protective gloves are used where some rotating surfaces are there. Many applications there are rotating knives are there. To get the correct result, which will be representative result. So, for that we use this Coupe test, and here rating is from 1 to 1 to 5 rating is given. Here number of cycles to cut through is determined as the cutting resistance index. If the blade is dull, then TDM 100 test is used. So, because in TDM 100 test is done on a fresh blade, but here if anything blade dulls, then we have to use the TDM 100 using ISO method, ISO 13997. But to counteract this dulling effect, so we have that this Coupe method, they have standard protocol that we will be discussing. Now, the test procedure, if you see, the steel circular blade of 10 centimeter like 100 millimeter diameter with defined hardness. Hardness is hardness value 700 to 720 hardness value. Okay. 700 minus 720 typically it is equivalent to 60 HRC. That blade is pressed onto the specimen at a contact load, as we have mentioned, it is a 5 Newton load. So, constant contact load, the blade is, this is the blade, circular blade, 5 Newton load is there, it is pressed. Then what happened? Then there is a rotation. So, 100 millimeter diameter blade and this will rotate, and during rotation they will also make the to and fro motion, back forth motion will be there, but the material is fixed. The blade oscillates, slides back and forth. Typically the stroke will be 50 millimeter, typically 5 centimeter back and forth motion will be there, while rotating the direction will be changed. So, the rotating direction also changes with the stroke. So, rotating direction will be opposite to the direction of the travel. Now, we can see here. So, this rotation is changing. Suppose this load with the circular blade is moving from right to left, and right to left when it is moving. So, it should rotate. So, this is moving in this direction. So, it will rotate in clockwise direction. So, that this there will be cutting action, and when it moves from left to right, the direction will change. So, this is the load, circular blade, this is a specimen and sample holder is there. So, we need a slicing action by changing this direction. So, the motion is reciprocating. When the blade changes direction, its rotation reverses, simulating the back forth cutting motion. So, that rotation also changes. Now, the procedure after testing, how the data is interpreted. First step is that the cut a standard canvas. Okay. We take a standard canvas, reference canvas is there. The blade cuts through the standard cotton canvas to establish a value Cn baseline. This is the baseline value. Then we replace that canvas with the specimen. The standard canvas is replaced with the testing specimen here. Then the test specimen is cut, the blade cuts through the test specimen, and we can obtain the number of cutting cycle Tn. Initially the cutting cycle was Cn for the standard canvas and Tn is the cutting cycle for standard test specimen. But after that we will again place the standard canvas. So, the canvas, same canvas we will put for testing once again, and the blade cuts through the standard sample canvas again to ensure the consistency. So, this is number of cycle is cutting cycle is C n plus 1. The basic idea is that there will be dulling effect during the cutting, but we are not replacing this blade always. So, from C n to T n, from first the reference sample to test sample. So, if we assume the dulling is there, and the similar dulling if we assume here for next canvas, second canvas C n plus 1. So, from there we can actually get some correction. So, directly T n as a number of cycle we do not take, but this is for reference. Then we calculate the relative cycles. So, that is I n, relative cycle is calculated. The relative cutting cycle of the test specimen is then calculated, which is I n. That is the result. Now, let us see the calculation. So, cut through end point. So, the test stops when the blade cuts completely through the fabric, and then immediately the machine will stop and there will be circuit completed. The total cycle is counted and recorded. So, total number of cycle before it cut through, that blade cuts through the fabric is recorded. Now, how to calculate the cutting index? The machine alternates the cutting the reference canvas first, then test specimen T under the constant load N, and then again the canvas. So, this alternate cutting will be there, and we record the data, and here we do not replace the blade using the same blade, okay, and load is constant. The cut index is calculated as the ratio of number of cycles on the sample to those on the canvas, that is the cutting index. So, cutting cycle ratio is that for each sequence I. So, there are different sequences. So, ith sequence the blade's sharpness is averaged out. So, we first average out the blade's sharpness from the cutting cycle of the canvas before and after the specimen, that is C n and C n plus 1. So, we get the average the cutting cycle for the canvas. This is for the canvas. So, C n is before the specimen number of cycle, and C n plus 1 is after the specimen. So, we try to calculate the blade sharpness. So, C n bar is the average cutting cycle of the two cuts on the canvas, and relative cut performance I is calculated from the cutting cycle of the test specimen Tn, and this is In for nth sequence. So, C bar n plus Tn by C bar n, that is a ratio we are calculating here. So, this is the cutting index In. So, that means it is a cutting performance here we are calculating here. Now, the same test is repeated for 5 times. So, for same specimen whatever we have calculated In. So, for 5 times we calculate I1, I2, I3, I4 and I5. The same thing is repeated 5 times. So, and then we average out this 5 tests to get final cut resistance level as In. So, In is the final cut resistance level. So, average of the 5 value. So, this is the cut resistance index we get. So, 2 specimens are tested for one sample and the lower In value is taken. So, In is calculated, that is for one specimen we are taking the 5 readings, and similarly 2 specimens are tested from different places. We get 2 specimens and whatever value lower value is getting. So, that is considered as the cut resistance level. That means, to have better protection, to get the more authentic reliable result, we get the lower value. Now, the performance level as per EN 388, it defines the 5 cut levels of In, that is index. So, this index is, which is ratio of the cycle by that with the specimen and the canvas, that we have already discussed here. The label, that level 1, if the ratio is more than equal 1.2, level 2 it is 2.5, level 3 5, more than 5, level 4 more than equal 10 and level 5 more than equal 20. The level 5 is the highest protection level. So, this way we can get the cutting index in Coupe test, which is followed by the EN 388 standard, and the level 5 being the highest cut resistance by Coupe test. Now, after understanding the 2 test methods, now let us try to understand the mechanics behind the cutting. So, in the cutting there are the process that it is a mix of the fracture mechanics, yarn geometry, friction and bending. So, in any cutting of any material, particularly textile material, there are different factors which affect the cutting process. This mechanics basically, first is the fracture mechanism, then yarn geometry related, then friction and bending. So, there are models behind this mechanics. There are two different models are there, basically main models. So, which there are other models also, but here we will be discussing the two important models. One is the energy balance model or it is called continuum model, and it is a general and physically rigorous model. Energy balance model, where we try to balance the energy, cutting energy, and discrete model, discrete form, where specifically for textile material, woven and knitted fabrics, where based on yarn. This is a practical, and that is it is a discrete model where there is no continuous yarn, there will be gap between the yarns. Like in non-woven, we can use this energy balance model, continuum model. For any other material, sheet metal material, we can use this continuum model, energy balance, but discrete model is basically it is practical for woven and knitted fabrics. First, let us understand the energy balance form. In energy balance model, it is continuum form, it is a general and physically rigorous, as we have mentioned. So, instantaneous cutting force F c, which is force applied by the blade, can be written as the sum of the rate of work required to create new surface plus dissipative and mechanical contributions. So, there this is the we can divide this energy into different components. So, cutting force into different components, this is a sum of the work required to create the new surface plus dissipative and mechanical contribution are there. So, let us understand in detail here. You can see this is the model FCX, this is the cutting force, okay. The force required to cut. So, total force required by the knife to cut through the fabric, this is FCX. So, this force is required for doing many activities. First is that it is a fracture is required. So, for a fracture, so fabric fracture force is there. So, here surface creation for cutting through. So, new surface is created, create a new surface. For that we need some force, like this is a material, thick material. When we are trying to cut, suppose this is a we are trying to cut here. Now, next process okay. Now, suppose a knife is penetrating, this knife has penetrated. Here internal surface, these are the surface which were created. Initially the surface was this, but new surface are created, these are the new surfaces are created. For that we need some force, and this surface is created after fracture. So, this work required to create new surface. So, this is F fracture is there. Okay. Next is the two counteract the yarn bending resistance. So, yarn gets bent, the bending will take some load, that is if bending is there, then friction. So, fabric and blade will slide because there will be relative motion, and that sliding resistance will require some force. So, F friction, that for clamping we require F clamping force. So, additional resistance from the tensioning or by holding the fabric. So, if it is under high tension, we need certain force, additional force, clamping, and some force is required for inertia, dynamic or inertial force. So, when it is basically it is important when high speed cutting is there due to yarn acceleration, okay, and it is negligible in case of slow cutting. When the cutting is slow, this is negligible, but for high speed cutting this is important. So, the total cutting force is distributed in fracture, bending of yarn, frictional force, clamping force, and dynamic or inertial force. So, now if you see the fracture force, this is the F fractural force, which is equal to G C W. What is G? G is the effective fracture energy, effective fracture energy per unit area, joule per square meter. W is the cut width, how much cutting is there, okay, and G C is the effective energy. Okay. Then the force, fracture force for bending or yarn deformation or fiber deformation ahead of blending, that is ahead of the blade. This is the bending force. So, U bend means the bending energy stored in the yarn before fracture, there is work needed to deform the yarn around the blade prior to the fracture. And next is that the distance moved by the knife, which converts the bending energy into the force. Next is the frictional force, force required to overcome the friction, mu N C. N C is the normal load, okay, that is the normal load, integrated contact normal load on the blade along the cut length, that is a normal load N C, and mu is the effective frictional coefficient between blade and the cut material, that is whatever material. So, that is the frictional coefficient. Now, next is the clamping tension, this is the work to hold the fabric. F clamp is du clamp by dx. So, this is the clamp induced work per unit advance. Okay. Per unit advance, what is the work required, additional work. So, force needed to overcome the pretension or boundary constraint. Last one is the inertia or dynamic terms. So, this is important only in case of blade is in high speed. So, it can be neglected in case of quasi static cuts. Okay. So, the final equation becomes F c equal to W g c, this is for bending, this is for friction, this is for clamping, this one is for inertia. So, from this balance we can calculate, if we know other components we can calculate one of the components. Now, the next model is the discrete model. So, discrete basically yarn based model, which is basically used for woven or knitted fabrics. For textile material it is used, it is often easier and more transparent model. Okay. This is to model the cut at as the breaking individual warp and weft across the blade, that is the discrete. After one thread breaks, then next thread it will come to the next thread. So, this is that is why it is a discrete one by one. Okay. Here is the relationship, F c is the force, cutting force, total force required by the knife to cut through the fabric. Here again Ny is the number of yarns during its path, number of yarns to be cut, okay, and Fy is the average force required to sever one yarn. So, average force required to cut the one yarn, and then if we multiply the with the n, then we will get the total force required to cut the yarn, all the yarns during the process. And F is again it is a yarn bending resistance, friction force, fabric blade sliding resistance, and again it is a clamp. Okay. Here inertia is not taken into consideration. So, this discrete model is basically a practical model, because the in a woven or knitted fabrics, if we see the cutting takes place one by one, after one thread then one. So, discrete model, this is the discrete model we have discussed here. So, Ny equal to W p y. So, Ny is the number of yarns to be cut by the blades. Okay. So, W is the fabric width along the cut. So, this is the these are the threads. So, we want to cut this direction. So, this is the total width, okay, W, and P is the number of threads per unit length. So, number of threads per unit length, that is ends per centimeter, peaks per centimeter, Okay. And from there this P y, if we multiply, we will get the total number of threads. And F y break is the equal to A y sigma break A y and sigma y break. So, F y break, this one is the, this is basically average force required to cut one yarn, okay. And this is equal to A is yarn cross sectional area, okay, yarn cross sectional area, and sigma y break is the breaking stress of the yarn. So, like, so breaking stress in Pascal here. So, from there we can calculate the average force required to calculate the to measure the average force required to cut one yarn. And next is that the bending and friction and clamping we can calculate as we have discussed earlier. And here the final relationship becomes F c equal to this multiplied by this. So, N y and F y break plus F bend mu N c as we have done earlier and F clamp. So, from this we can calculate the actual force required for cutting the fabric, particularly woven and knitted fabric, yarn based fabrics. So, these two models we have discussed. So, that is load balancing. Now, let us discuss the factors which affect the cut resistance of textile material. There are different factors which influence the blade to fabric cut resistance. Many factors are there beyond just the material's intrinsic characteristics. So, materials characteristics is important. So, like if you use the high performance fiber or steel, stainless steel, they will have their intrinsic strength, intrinsic cut resistance, but the cut resistant characteristics of the fabric can be manipulated by different other factors. So, here we will try to discuss all these factors. So, understanding these factors help in designing better cut protective material. So, we must understand whether it is a thread density is important, yarn twist is important. So, all other parameters apart from the material. The key factors include, first is the blade geometry and angle of attack, that is very important. So, we have the same fabric, but if the blade geometry changes, the cut resistance property will change. So, there are different types of blade geometry. You can see here there are different types of blade geometry. So, each and every blade will result different types of protection. So, standard testing is one, getting a standard fabric is one, but if we change the angle of attack or geometry of blade, the performance may vary. At certain set at 90-degree attack, angle of attack, a fabric will perform in different way than a certain different angle of attack. Okay. So, it describes how the blade is oriented and move relative to the material. So, a person may be hit at any places. Okay. So, here we can see, so this is overhand stab, overhand, say angle 12, this is overhand stab, and underhand stab which is say 5, this is a 5. So, different types of stabs are there. If someone is attacking from the top, from the bottom, so different types of attack angles are there. So, depending on the that attack angle or type of the knife, so different types of knives are there. So, the severity changes. So, that is blade geometry and angle is important. Then normal force, in standard we apply certain force, like in Coupe method we apply say 5 Newton force, but that is not true always. In actual practice someone will apply a different force, or in use in actual application during work the normal force may be different. So, perpendicular force pushing the blade into the material, that is the normal force, that affects the cut resistance characteristics of a particular fabric. Then cutting speed, whether it is a slow speed, quasi static, or maybe it is a dynamic cut, very rapid. So, depending on this speed the cut resistance value changes. So, here we can see this is the direction, this is one direction where the tip only is in contact and it is cutting, and cutting at slow speed, or the total blade is in contact. So, cutting angle is there and it is moving at slow speed, and if we change the speed, cutting speed, the cutting performance will change, cut resistance characteristics will change. The fourth factor is the fiber orientation and fabric structure. So, there are other factors and detailed discussion we will continue. So, what we have discussed, the 3 factors already we have discussed. One is blade geometry and angle of attack, next is the normal force or pressure applied and cutting force. So, these are the different types of cutting speed. So, quasi static or dynamic, and next is that fiber orientation and fabric structure, and that we will discuss in the next class. Till then, thank you.